1960, Sir Derek Barton went on holiday. So, where do chemists go on holiday? Well, for Sir Derek, it was the Research Institute for Medicine and Chemistry. What did he do on holiday? He studied the synthesis of steroids. But why? As the potency of a natural product class gets discovered that can't be made easily, a flurry of interest occurs from chemists coming up with different solutions to the synthetic challenges. During the 60s and 70s, steroid chemistry was all the rage, with 1960 seeing the first oral contraceptive approved by the US FDA. More specifically, Sir Derek sought to solve a problem of converting a readily available steroid into an uncommon steroid. This is called partial synthesis, starting from one complex natural product and making another. Incidentally, total synthesis is where you start from simple small molecules to make a complex natural product, not applicable in this case. The steroid he started with was corticosterone acetate. The steroid skeleton has 4 rings that are fused with each other. They are described as ring A, B, C, and D. Now, Barton wanted to manipulate the methyl group at the fusion of rings C and D. This is a massive problem. Converting alkanes into anything else is difficult. This methyl group of this steroid is exemplary of this dilemma. The methyl group is not in close proximity to heteroatoms. In this steroid, that would be oxygens. So this region is comparatively unpolarized, making the formation of charges or even partial charges in order to convert the alkane into something else very challenging. To make matters worse, this functionalization must occur only at this site. It must be selective. Barton's Nitrite Ester Photolysis solution was extremely elegant. He used radical chemistry that relied on neutral radicals, so no charge formation is required. And for his selectivity, he utilizes the remote alcohol also on ring C to activate the CH bond. Let's focus in on ring C. Now, imagine it in 3D and then strip away most of ring C just to look at the key portions involved in this chemistry. To start with, we use heterolytic chemistry, where 2 electrons involved in the bond forming or bond breaking come from and go to the same location. We deprotonate the alcohol with a base such as pyridine. The resulting alkoxide attacks the nitroso chloride to form our key nitrite ester. Now for the clever stuff. The molecule is irradiated, and we can homolytically break the nitrogen-oxygen single bond. So the 2 electrons of this bond go to different locations to provide a nitric oxide and an oxyl radical. This radical abstracts a hydrogen from 5 atoms away. It's called a 1,5 hydrogen abstraction. Not 1,4, not 1,3, nor 1,2. As 1,5 offers a most stable 6-membered ring chair-like transition state. The result is the return of the alcohol, but critically, the methyl group, thinking in terms of the global steroid, is now selectively a radical species. The radical of the nitric oxide homolytically reacts with it, with 2 electrons making a bond coming from different locations to provide the nitroso intermediate. This key carbon has gone from being unfunctionalized to functionalized. Now, with heteroatoms attached, we can use a variety of heterolytic chemistry, deploying partial and full charges to modify this carbon into lots of different functional groups as we may need. Initially, it is naturally tautomerized into an oxime, and in this case, with the addition of acetic anhydride and pyridine, followed by aqueous sodium nitrite, we get a natural mixture of the hemiacetal and the hydroxyaldehyde, described in terms of the global steroid as aldosterone.